Hello, I am audible. Yes, please. Anyone?
Yes, sir, audible.
Okay, okay, thank you. Let's wait for 2 3 minutes, then we'll start. Whether the hello, the slide is visible to all of you?
Uh, Now it is not visible, sir.
Okay,
Earlier it was visible earlier.
okay, let me check. Now visible?
It is visible now.
Okay, okay. Sometimes the network problem here, so that's why, but not that much problem. Okay, let us start. Okay, someone asking about the registration part. Me and my friend trying to register the exam. Matthew, you can drop the mail to NPTL because I have not any this kind of control on that, so I cannot do your help. So it's better to you contact NPTL member. Okay, now we will start. I'm audible, no? Hello?
Yes, sir, audible.
Okay, now we'll start. So, welcome all in the week 5 fluid mechanics live TA session. This is the problem solving session. I'm from IT Guwahati. My name is Om Prakash Mulya. Okay. The week 5 content was about the problem solving session, that is the fluid static problem solving session and the conservation of momentum and the Bernoulli's equation. Okay. From the previous class, last Monday, some student was asking about the pitot tube concept and also Bernoulli equation concept. So let us discuss first some basic concept regarding the pitot tube and Bernoulli's equation, and also some student was asking about the pipe roughness, how affect the velocity and pressure. We'll discuss. Then after we go for the problem solving. Okay, the Bernoulli equation is visible. Please tell anyone.
No, sir, we don't have any Bernoulli's equation on the.
Or you see na blackboard, blackboard.
No, it is not come actually. It is not focused yet. Uh, we are just finding the welcome in week 5.
Okay, okay. Why it is not moving? Let me share again. I think some. Let me share again. Now the slide is moving.
Uh, yes, sir. It is now. It is visible.
Okay, okay. So the week 5 was about the application of fluid statics and dynamics. So lecture 1 was about the fluid static application, and lecture 2 was about the conservation of momentum. The all session was about the problem solving session. The last one was about the Bernoulli's equation. So I think Bernoulli's equation is visible to all of you.
Yes, sir. It is, but it is bit small actually.
Okay, okay. Now I'll try to write something. No problem. Let us first discuss the concepts.
Yeah, it's okay. It is visible. Not
Yeah, and from previous class, one student was asking about the Bernoulli's and Pitot tube and all. We'll also discuss about that. Then we'll move for the question answer because concept is very important. So Bernoulli's equation in terms of head, that is the P by rho z plus V square by 2z plus Z is equal to, you can say, constant. Uh, Whatever I am writing, it is visible now.
yes, sir. Visible.
Okay. So, or also you can tell the combination of all known as total head. Okay. If this equation you want to write in term of pressure, so first we'll discuss what is this. This term whole indicate the pressure term, and this one indicate the kinetic energy, and this energy indicate the this, I mean Z here indicate the elevation head. So if you want write this equation in this form, let us write here, like I want to divide rho z throughout the equation. So if you divide by the rho z, what will happen? Rho z, not multiply by rho z, what will happen? That is the rho z, this rho z and this rho z will deduct it. So what remaining? The p by p, only p here, and v square by 2 and rho, you can say, and rho gz equal to, again rho g is the constant, so again the here constant. So this equation was in terms of the head, like pressure head, velocity head, and the elevation head. This equation in terms of the pressure, only pressure, not in terms of head. The unit of this equation of each term is the Newton per meter square. So we'll use this concept in the coming slide. Okay. What was the equation? P by, only P, not P by, and rho V square by 2 plus rho Z Z equal to constant. Okay. This, as you see here, this P indicate the static pressure, and V square by 2Z indicate the, if someone want to the screenshot, please take. If you want to take the screenshot, you can take the, no problem. For this, I am following the single Simbala book. What sir was suggest to all of you, that book I followed. V square by 2z, rho V square by 2z indicate the dynamic pressure, and rho Gz represent the hydrostatic pressure. And don't be confused here. The rho ZH, you know, as you study in the hydrostatic rho gh in the class of hydrostatic. This is different. This is increasing with the, let's say, here water in this tank. This pressure is increasing with the depth, but this one is a different. This is depend on the datum. Let's say if you take the datum at that location, I will explain what is figure. And if you take the datum at that location, so this will decrease with the depth, and rho gh will increase. So don't be confused with the hydrostatic or the whatever you study the concept in the hydrostatic. So this is the rho gz. Now we move on the next thing. So this is the pipe flow. What the figure is indicate is a pipe flow, and one pitot tube is inserted at that location. That is the pitot tube, and for measuring the piezometric, for measuring the pressure, that is this term. What we use the piezometer. We use piezometer. A pitot tube, what measure? Pitot tube measure the both things. That is the this things and this thing. That is the velocity, your velocity pressure. That is the dynamic pressure. So pitot tube we use for basically we use for measuring the pressure, that is the static pressure, and as well as the dynamic pressure. If you take here datum, then your rho z is equal to 0. So that's why in the previous question was framed like that. Your pitot tube used for what? So pitot tube we can use for steady and dynamic, as you where is it written? Yes, the sum of static and dynamic pressure, also called the stagnant pressure. So pitot tube you use for, generally the question is asked was asking about the lots of examination, the pitot tube used for measuring the velocity. Okay, but we can also measure by using the pitot tube a stagnant pressure. A stagnant pressure nothing but the combination, that is the addition, that is the sum of static and the dynamic pressure. So I hope the pitot tube concept clear to all of you. And one question was also about the static pitot tube and pitot tube. So for that, the static pitot tube and the pitot tube, there is not much difference. So for that, you can follow the this description whatever I have written. So please take a screenshot. If you want a screenshot, please take. Then we'll move for the question answer. It's done. Now the another, this static pitot tube also basically one, this figure is indicate what, if you are going to insert some insert the your instrument in the pipe, so make the properly hole. If you not make the properly hole, what will happen? You can see the measure. Here is the high, this one is the low. If you make the properly hole in the pipe, your reading will be correct. This thing indicate. Now the we coming on the roughness of the pipe. Hello.
Yes, sir. We have,
Yeah, it is visible, no?
yeah, visible.
Okay, and if you want a screenshot, anyone can take, no problem. So roughness, basically the pipe roughness. So the pipe roughness, basically roughness is affect the both velocity and pressure. The previous day was one student was asking the how the roughness pipe affect the pressure and velocity. Is roughness affect the pressure or velocity? No, roughness is affect the both pressure and velocity also. Due to the roughness, due to the pipe roughness, the pressure is dropped along with the pipe, and due to the roughness, velocity is reduced along with the pipe. So this is the final about the your how the roughness affect the pipe, whether they increase or decrease. Okay, now you can take a screenshot this also. What is written here in the engineering and fluid dynamic, these effects are quantified. These effect means the roughness effect on pressure and velocity, quantifying using the various equations such as Darcy's Weisbach equation or Colebrook-White equation, which relate the factors like pipe roughness, velocity, flow velocity, and pipe diameter and the flow properties to calculate the pressure drop and flow rate accurately. So these are the actually previous, these are the concept about the previous questions. So now let us move on the question answer session tomorrow. So I hope the question is visible to all of you. The question number one and question number two
Yeah, visual,
is
sir.
visible. Okay, please go through the question and write your answer in the chat box. So the first question is about in which of the following measuring device Bernoulli's equation is used? Venturi meter, orifice meter, pitot tube, all of them. So basically, week 5 was about the application of the Bernoulli equation. So this question is about the by using the Bernoulli's equation. Basically, no, this question is framed in the different way. In which of the option we can use the Bernoulli's equation, or which instrument was designed based on the Bernoulli's equation? This question was asking. The first option is the Venturi meter, second one is orifice meter, and option C is about the pitot tube, and option D the all of the above. Okay, please everyone participates in the question answer session. Write your answer in the chat box. So Pradeep is telling the option number D. Okay, let's see. Yes, please everyone write your answer in the chat box. Okay, whatever you are understanding, please write your answer on that basis. Then you can easily, if you will not try give the answer, this is the very small questions on very basic questions. Okay, Ashok is telling the D. Okay, majority of student is telling the option number D is correct. Okay, So the option number D is yes, correct. We design the venturi meter, orifice meter, and this thing, a pitot tube, basically on the basis of the Bernoulli's equations. Basically, we can apply in the pitot tube concept Bernoulli's equation. Oh, please follow the question number 2. Go through the question number 2. In case of a closed cylinder vessel, in case of a closed cylindrical vessel selected at top and actually not visible me also, let me go on the yes. In the case of closed cylindrical vessel, sealed, not select, sealed at the top and the bottom, the volume of air before rotation is what? Is the same or dot dot the volume of the air after. Like this is the one cylindrical vessel and the tightly packed in the bottom as well as on the top. And this is the first case. And the second case is what? The same, the cylinder is same, just I am drawing for sake of your understanding what question is asking. This is the okay. And now you are going to move, going to rotate fluid. And what will happen in the K in the volume? It will be equal or it will be reduced or it will be more or less what? Please write your comment in the chat box. Okay, Matthew is telling Pradeep and also call telling the option number C is correct. Yeah, because it is sealed. If it was not sealed, then different. Maybe it is asking about the air. If it was not sealed, then may chance to like in case of gas, uh, it will be easily moved out of the cylinder. So now coming on the next question. The question number 3 is about a flow has diverging straight streamlines. If the flow is steady, the flow option number A is a uniform flow with local acceleration. Option B has a convective normal acceleration. Option C has convective tangential acceleration. Option D has convective normal as well as tangential acceleration. So this is a bit conceptual question. Please write your answer in the chat box. Write the equations, whatever the equations you know about the convective acceleration and local acceleration, write in your copy and do some analysis whether this for a straight streamline, whether the normal acceleration or tangential acceleration or both possible. Please write your answer and the local acceleration also. Write your answer, then we'll move for the concept behind it, the question. Okay, for question number 3, Pradeep is telling the option number D. The flow has convective, normal as well as tangential acceleration. Oh, let's see whether the option number C and D what were. You just remember the streamline is a straight. I have some note about it. What is streamline? I have one slide about the detail, the concept behind the streamline. So I will show. First you write. Please everyone write the answer. Whatever you are getting. Like Pradeep is telling the option number D is correct. Whether the option D is correct or whatever you are getting, you just write. It may be correct. It may be wrong. With that you can easily, with that approach you can solve the questions, because here you are not getting any marks regarding that. So here at least you participate whatever you are understanding about. Okay, the Matthew is telling the option number A is correct. Ashok is telling the option C. Okay, let me explain. Then we'll go for the question number 4. Okay, let us assume a pipe flow. Water is entering from this side. You always, when you show the diagram of flow anything, you show the arrow from where it is coming and which direction is going out. Okay, you just, in the question what is given, the streamline, straight streamline. So you just draw the straight streamline like that. These are the straight streamline. And one thing you know, the acceleration, let's say this is the x direction and this is the y direction. So you, if I want to write the acceleration in the x direction, what is the u del u by del t plus, I think you all have remember, u del u by del x plus v del u by del y plus w del u by del. So this equation here I have taken only 2, so you can eliminate this last term, no problem. In the question is given the flow is steady, so this is 0. Now the streamline is straight. Streamline is straight means what? There is no normal component of the velocity. There is no normal component of velocity. So the normal acceleration is 0 in case of straight streamline only. That is, the water is flowing only, the convective acceleration here, like okay, now I want to tell you, del u by del t is known as local acceleration, and these all term in the combined known as the convective acceleration. So because the flow is steady, so local acceleration is 0 given in the question, and straight streamline, or there is no normal component of the velocity. So normal acceleration is zero for a straight streamline. Only what is remaining, the convective acceleration. So for this question, the flow has diverging straight streamline. If the flow is steady, the flow has convective tangential acceleration. So option number C is correct for this question number 3. Please go through the question number 4 and write your answer in the chat box. Yes,
What is
please.
diverging? There is something called diverging.
Diverging means here nothing but let us let me come on the PPT. Diverging means is basically your flow is assumed like that. Here the diverging term is not, I think, bit you may facing the confusion. The diverging like here flow is coming from this side, so this flow, due to this flow in the pipe, and you can assume anywhere, the flow is moving like that in the straight streamline. Diverging thing here is like that, not something it is related to the mathematics. Diverging thing, some flow is coming from another source, and when it is entering in the pipe or anywhere, it follow the straight streamline. This is the meaning here. Okay, please go through the question number 4 and write your answer in the chat box. Whatever you are understanding, this the question 4 is about if flow has parallel curved streamline and is steady. Here is also the case of steady, but in the previous one, streamline was about straight, but here streamline is curved. So whether the local acceleration or convective acceleration or both. Okay, Vidya is telling the option number D. Okay, let's see. And when you solving this type of question, you please select the most appropriate. Maybe the two option may be the correct in the all of whatever the 4 or 5 option is given, but you select the most appropriate. If option is given the only one option you choose, then you select the most appropriate. Whatever the most appropriate option is there, you can select on that basis. So for question number 4, Ashok is telling the C. Okay, here the study term is there, so you just assume, you just think whether the local acceleration will be considered or not. Regarding that, I have a note. I have one slide, so I will show just another. I am waiting for 1 minute. Yes, please write. The other people write your comment in the chat box. What are you thinking? Whether option A, B, C, D, which one is correct? Okay. Matthew You is stating the option D, option A. Okay, let me move on the PPT. So before going on the explanation, just I want to show some. So I want to take one more slide. So let us discuss some definition. So it is visible now, all of you.
Yes, sir, visible but bit small actually, but okay, no problem. You can still read it.
Let just now it is visible, clear.
Better, sir. Yeah, better.
Okay, it's fine. So what is written here? The what is convective acceleration? First definition of convective acceleration. That is the convective acceleration refers to the change in velocity of fluid particle as it moves along its streamline. It's a result of change in velocity, magnitude, and direction as the particle move from one point to another point within the flow field. You can assume some open channel, or you can assume the pipe flow also. These are the streamline. You can just, these are the streamline. Sometimes the streamline also curve. We'll discuss then again. So this is the basically telling the definition is the convective acceleration refers to the change in velocity, how the velocity is changing of the fluid particle when it moves along the streamline. And the straight streamline, let me first we move on. Second definition is the normal acceleration. We'll see. I want to see the first normal acceleration, then we move on the straight streamline. The normal acceleration is the important of the acceleration that is perpendicular to the velocity vector, of the fluid particle. It's responsible for change in the direction of the velocity vector while the particle is moving along its path. What is telling? In some time the your streamline like that, letting the curve sometime like that also. When let's say assume some this type of body in the flow direction, and what will happen, your streamline follow the like that path.
Sir, your cursor is not seen actually.
Oh, it is not visible.
No, no. Except the
Okay.
definitions, you don't see anything.
Oh, so it will be, you cannot understand. Okay, just I want to write something. Now it is visible. Yes, please, anyone?
It's visible.
Okay, I think in the full view mode it is not visible. Okay, no problem. So convective acceleration is that, let us assume some open channel and cylindrical thing. This is the, you just for sake of understanding I am taking the straight streamline. As your fluid particle moving from one place to another place, how the velocity changes along the streamline, this is indicated by the convective acceleration. The normal acceleration, what is indicate? This is the normal acceleration. The normal acceleration is the component of acceleration that is perpendicular to the velocity vector of the fluid particle. The component of acceleration that is perpendicular to the velocity vector. Let us assume one curve is there and your velocity vector is what is, draw a tangent along the streamline, it is given the velocity vector, right? So this is the perpendicular thing, and this thing gives the horizontal thing. So what is telling, the acceleration due to this component is known as a normal component, normal acceleration. Due to this, the how this component of velocity changes when the fluid particle flow from one place to another place. So this thing is indicated by the normal acceleration. As you can see, in case of a straight streamline, there is no, when you draw the tangent along the straight streamline, what will happen? Only one direction of flow, not in the lateral direction. So but in this case, in case of curve, there is a component because your velocity vector having the some inclination. So inclination with the horizontal. So what is conclusion here? In case of curve, normal acceleration is always there. In case of curve streamline, and when curve streamline is happening in case of, if you see the actual flow, let's say you just assume the river. First, I am trying to interpret it by the physical structures and assume one breeze pair is there in the river. Lots of breeze pair, but for sake of understanding, one breeze pair I have taken. When the flow is coming from this direction, so your flow behave like that here, like that. So here is a curve streamline, at that location is a curve streamline. I am showing to you on the top view. You just imagine I am showing you the top view. Okay. So in that case, the normal acceleration is exist in the curve streamline, not in case of straight streamline. So this is the definition. Now, what is a straight streamline? Along a straight streamline, there is no change in velocity direction. Yes, you can easily understand by the definition. Makes sense. Consequently, there is no change in the direction of the velocity vector, and thus the normal acceleration along the streamline is zero because of what I have given you the concept behind it, how the streamline normal acceleration is zero along the straight streamline because there is no normal component of the velocity. The fluid particles are moving in the straight line without any change in the direction. Now coming on the curved streamline. In the case of curved streamline, the fluid particle change their velocity direction as they move along the curve. When the fluid particle moving like that, the velocity, you know, the velocity is having the direction as well as magnitude. If anyone, velocity having two things, they are magnitude and also direction. If the magnitude is 4 and direction is this direction. Flow is moving in this direction. Now I want to take the second case. The magnitude is still is 4, but direction is like that. This is 1 and this is 2. Direction is like that. So your velocity changes, because if any one parameters is changes, whether direction or magnitude both changes, then obviously, but any one parameter it changes, then your velocity changes. So what is right? What is written here? In case of curved streamline, the fluid particle changes their velocity direction as they move along the curve. This is clear to all of you, I hope. This implies that the velocity vector is changing direction, leading to non-zero normal or normal acceleration along the curved streamline. The curvature of a streamline is directly related to the magnitude of this normal acceleration. So whatever we have discussed, this is written. This is written. You can take the screenshot. No problem. So now coming on the fourth question, you can take the screenshot of this also. This is the same thing is given. You can take the screenshot of both first and second. This will help you understanding. Now the question number 4. A flow has a curved streamline. Parallel curved streamline means what? The all streamline behave like, if streamline is this, then the streamline behave like that. This is the parallel. Okay. Then what is, a flow has a parallel curved streamline and a steady. If there is steady flow, then your time term, that is the du by dt, is 0, because the steady is given. So local acceleration, where is the here is local option is neglected. Local acceleration in this is neglected. And whether the tangential convective acceleration or the normal convective acceleration, so only two option is there. But in case of a straight line, only the convective acceleration is exists. So best appropriate option is here. The option number D is correct. The normal convective acceleration is present in case of curved streamline. Here the both is present. You normal as well as the convective acceleration is also there. But as per the option given, you go on the option number 4. Now the question number 5 is visible to all of you. Please,
Yeah, visible.
okay, please go through the question number 5. After this, we'll have some break of 5 minutes. The question number 5 is about the flow in a river during the period of heavy rainfall. Assume in your area one river is there and heavy rainfall is occurring. What is happening? The flow will study. If you know the definition of steady, uniform, non-uniform, one-dimensional, two-dimensional, three-dimensional, then you can easily give the answer. Otherwise, it is very difficult to all of you. So please write your comment. Everyone write your comment in the chat box. Okay, for question number 5, option D. Everyone telling the option D is correct. Okay, so Matthew, Vidya, Sarif, Pradeep. Okay. So for question number 5, the flow is unsteady, non-uniform, and three-dimensional. Yeah, it's okay. It's a very easy question. Now please go through the question number 6. If the flow is irrotational as well as steady, then it is known as what? The flow is irrotational as well as steady. These are the definition basically. If you know the definition, then you can easily guess the answer. Rotational thing and the irrotational thing, sir was explaining in the very well concept, the concept of virtual ball. If you know the virtual ball, what sir was telling, you can easily understand what is rotational and irrotational. But here is the case of definition, whether the non-uniform, whether the one-dimensional potential flow, and none of the above. Okay, for question number 6, Pradeep is telling the option B, Ashok is telling C, and Matthew is telling the option B's. Okay, see. Let's see. Yes, please. Anyone want to give the answer? Okay. Option C. Okay, okay. Anyone want to give the answer? Please write your answer. Within 1 minute, I will declare the answer. So for the question number 6, option what C is correct. If a flow is having the characteristics irrotational and steady, that type of flow we know the potential flow. I think I have some more here. P. It is visible. I think not clear visible. Let me.
Yeah, visible, sir.
Okay.
Now it's visible. Sir, why should we call it potential flow? What is the reason that it is called potential flow? Why
Yeah.
potential? What is
Yes.
the reason that it's called potential flow?
Okay. 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 That's why I have put it here. The velocity potential is a concept used in the fluid dynamics. So please first, if you want take a screenshot, you can take. After this concept, we'll take some break, 5 minutes. So the potential flow is nothing but this is the basically the characteristics wise we know the velocity potential is a concept used in the fluid dynamics to describe the relationship between the velocity field and the scalar function known as the velocity potential function. So basically it is a mathematical which potential flow is nothing but by actually definition is like that framed like that or in the mathematics way what is the it simplify the analysis of incompressible irrotational flow which are basically whatever here equation is given, this equation is derived based on the flow simplify the analysis of incompressible and irrotational flow, and these are the what this thing we know the potential thing here for this case, and this is the function of basically velocity UVW, you can say the velocity. So that's why we know the velocity potential function. There is a nothing any the mathematics concept behind it why we know these things as the potential only for namesake, or we give the name of the potential function like the irrotational flow. So we'll move on the next, which are follows where the flow density remains constant and there is no flow rotation. Okay, in an incompressible rotational flow the velocity field can be derived from the scalar function called the potential velocity potential usually denoted by the Greek letter pi. You know the all. The velocity potential is defined such that the velocity component UVW of the flow and can be obtained by taking the partial derivative of the velocity potential with respect to the Cartesian coordinate. So this is a nothing but the way if you some function is there like function is about the UV, the function included the UVW term. So for calculating the U, what you will do, you just take the differentiation of this whatever they given like for let's say the 2u square plus 3v square plus just for sake of understanding I am taking here 48 square 4w. So your u what you can differentiate in the x direction this function you can get the u direction velocity, differentiate in the y direction this function you can get the velocity in the y direction, differentiate this function in the z direction you can get the w component of the velocity. So basically this is the nothing but is related to the mathematics term your water flow in the channel and whatever in the pipe, the equation of these streamline somehow if you are able to the how the flow is happening in the channel or pipe, if you able to formulate in terms of phi, that is the function of x u v w, then you can easily calculate the component of the velocity. These are the concept. So the question number 7 and 8 we'll see after 5 minute break. Oh, Please wait just a minute. I think I have lost my connection. So just I have joined with my mobile. So please wait within 2 minutes. Or we can take the 5 minute break. Uh, in 7:20, uh, after 7:20, we'll solve the problem. So you can also take the 5 minute break. If anyone here, please solve the question 7 and 8, and you can write your answer in the chat box. Yes, please. I am audible.
Yes, audible.
Okay. Please. Okay. Your answer is C. Okay. Let's see. Please, everyone, write your answer. The question number 7 is about the momentum correction factor beta. The momentum correction factor beta is used to account for what? The change in the direction of flow, the change in the total energy, the non-uniform distribution of velocities in inlet and outlet section, the change in the mass rate flow. For that, I have some one or two, three lines I have regarding the momentum correction factor. I will show you. Please write your answer. Everyone, please write your answer chat box. Whatever you are getting about this question in your mind, please write whether option A, B, C, D correct. Okay, I will not take much time. So for question number 7, your option number C is correct. It's okay. For question number 7, option C is correct. The momentum correction factor is used to account the non-uniform distribution of velocities in inlet and outlet section. Okay. Now the question number 8.
So you need to show something, sir.
Yeah, I want to discuss. Yes. What is written? I have two paragraph about that. In the in fluid dynamics, you can take the screenshot also. In the fluid dynamics, when dealing with the situation where the flow is not straight or uniform, or when there are change in the flow direction, the actual momentum carried by the fluid may not match the momentum calculated using the perfect conditions. What is written here? Like whatever we have the equations, like let us say assume the pipe here, or you can also assume the open channel. No problem. Let us, for sake of understanding the pipe, water is flowing in the pipe like that. This side leaving. So using the mathematics equation, like how the water is flowing, we have derived some mathematical equation. Using these mathematical equation, we calculate the velocity is, let's say, something x quantity, x magnitude, and pressure something y magnitude using the mathematics equation. But in actual, maybe some, or you know, the momentum formula. Momentum is what is mass into velocity. So maybe in case of actual, this may be increase or this may be decrease. It's depend on the condition. So minimize these things, or considering these things, we use the momentum correction factor by calculating the mathematics is different thing. If we uh, observe something in practically, it may not be exact as per the whatever you have calculated in the mathematics. So if you go for the designing something, so you need some factor of safety. So for, as you can, let's say your velocity is coming x, but in the actual case it may be increase or decrease. So that's why we take the some correction factor, which suppose we are try to uh, go with the practical. We try to approximate the practical case. So that's why we take the, and what is written here in the another line, this discrep- this discrepancy arises due to the factors such as pressure gradient. Pressure gradient is what? The del p by del x. Like if you consider here x in this direction, so how the pressure is changed with, like the, what is the pressure here, what is the pressure here, what is the pressure here, what is the pressure here. So as increase, as your direction is in x direction, you are moving from x direction. So how the pressure is changing, this is known as the pressure gradient. So change in pressure with respect to change in x. This is written here. Pressure gradient, friction, and the change in velocity direction. Now, the momentum correction factor is introduced to adjust this discrepancy and provide a more accurate estimation of the actual momentum transport. It's commonly used in the various fluid flow calculation and engineering analysis, such as when the dealing with flow through pipe and vents, flow around corners, and the flow past obstacle, like maybe your breeze pair in case of the open channel flow, or maybe in case of pipe something, some valve kind of thing, if valve. So this type of any obstacle in the flow, then we can we use this type of concept for that. So now coming on the question number 8. Pradeep, you got it?
Yes, sir, no problem. Yes,
Okay.
good.
So for question number 8, please go through the question number 8 and write your answer. Everyone write your answer in the chat box. For the continuity flow, the equation is given, del u by del z, del x, and del v by del y, and del w by del z is equal to 0. Whether this equation is valid for a steady flow or incompressible. It is valid. Option B is that it is valid for the compressible fluid or whether the flow is steady or unsteady. Option C is that it is valid for a steady flow, whether the compressible or incompressible. The option D is valid for ideal fluid flow only. Here the definition is required. If you know the definition of compressible or incompressible, in case of compressible flow, the density is constant, not constant as the flow moving in the flow domain, but in case of incompressible flow, your density is constant. So, incompressible flow, you may not consider the density in the equation. So here you can think like that, you can give the answer. Okay, two participants is telling the option C. Okay, please write your answer. Another student, the continued equation for question number 8. Please write your answer. Okay, Ashok is also telling the option C. Okay, Matthew is telling option A. It is not valid for unsteady and incompressible. Okay, let's see. Okay. Okay, no one I think want to give the answer. Now I want to discuss. For question number 8, basically the equation is given like that. Or del u by del x, del v by del y plus del w by del z is equal to 0. So in this equation there is no density term is given. So already assumed here the density is constant for this, whether let's say assume flow in the pipe and flowing like that, and let's say the water, liquid water, so flowing like that, and this flow equation for this flow follow this equation. So for this fluid, any fluid is flowing in the pipe, if follow this equation, then density will be constant, because in this equation there is no consideration of density, as you see. So density is constant. So in case of incompressible flow, density is constant. In case of incompressible flow, density always rho is constant. Okay, so basically this option is eliminated because here the compressible flow is given. Okay, here the temporal term also not given. Temporal term is means what? Del u by del t, del v by del t, and velocity how changes with. That is the any variation of any flow velocity variation with respect to time is not given in this equation. So this equation, that is the del u by del t, that is the velocity change with time is equal to 0, is assumed in this equation already. So steady case, this is mainly the steady case where the unsteady is written in this option 1, it is eliminated. Option B is already eliminated. So this equation is valid for what? Valid for the incompressible fluid because rho is constant. Are you as visible in the equation? There is no density term is considered, and basically this is the continued equation. In continued equation, we not consider any the temporal term. Basically, when we derive the uh, this acceleration term, in that case we have assumed the temporal, that is the local acceleration and the convective acceleration. But in case of continued equation, so here in the unsteady is given, this should not supposed to given here. So option number B is correct for that. It is valid for incompressible and flow is steady, not unsteady. So you the option is go for question number 8. The option B is correct. Now we'll move on the question number 9.
So is the incompressible word is incorrectly mentioned here? It is not correctly mentioned here.
Which one?
This in the number 8, say compressible or incompressible is there. So the incompressible word should not be there, I think. The on-steady word should not be there in this.
Yes, yes, yes. For question number B. Some typing mistake maybe
Some
sometimes.
type mistake, yes.
Yes, please. For question number 9 and 10. Here the 2 2 times 9 is written, not considered in the question. Which of the following, question is started from the which of the following. Which of the following is an example of free vertex flow? What is free vertex and the vortex flow? I have some slide I will discuss. First you attempt question number 9. Which of the following is an example of free vertex flow? Uh, the option is given: a whirlpool in the river. Option B: the flow of liquid through a hole provided at the bottom of a container. Option C: the flow of liquid around a circular bend in a pipe. Option D: all of the above. For question number D, Francis and Ashok is telling the for question number 9, option D correct. Okay. Sarif is also, Pradeep is also telling the option D. Okay. But in spite of that, I will explain the what is free vertex and vertex flow. And if you will take the screenshot, you can take. Please, everyone write the answer. The another participants, please write your answer in the chat box. Okay, if anyone want to write your answer, please write. Then I will discuss. Okay, now I want to explain. So basically, what is vertex flow and all? Let's move on the next slide. The slide is visible. Next slide is visible to all of you. Yes, please. Anyone tell?
Yes, sir, very
Yeah.
clear.
Okay. So vertex flow is nothing but what is vertex flow? Let's read the paragraph. The vertex flow is also known as the rotational or swirling flow. That is the that type of flow. Your flow is this is considered the open channel or pipe. When the flow is moving in this direction, flow is coming from anywhere as entering in the pipe. Flow is moving along the length of the pipe is rotating as rotating. That is the fluid particle or fluid packet, you can say. The fluid particle moving uh, along the length with some rotation. This type of flow is known as the vertex flow. What is written here? The vertex flow is a phenomena in the fluid dynamic where the fluid particle within a certain region of flow field rotate around an axis or a central point. Basically, the all x-axis, let us assume the x-axis, let us assume the y-axis for sake of understanding. So maybe vertex like that in the vertical direction also vertex is possible, or if you take the jet direction, in the jet direction also rotation is possible, in the x direction also the rotation is possible. So this is the meaning of here, the axis of rotation or central point. The creating a spherical motion means like that, the spherical motion, the rotating motion. This type of flow, what is happening?
So, does it mean that it need to rotate in both three axes, about three axes,
Yes, yes.
or it you only need to rotate in about one axis? I mean, if it's moving in a pipe, I mean in x direction, do or it need to rotate in both three axes.
Yeah, yeah. No, I will tell you. I will explain. Sure. Just wait a minute. Let us take a new slide. Let us assume some open channel flow case. There is a high flow, or here is this one is a x direction. You can, you just imagine this is a river. Okay, and you see you are seeing the river from the top. These are the wall. This is the top view I am showing you. These are the top view. These are the wall of side bank, actually river bank, and this is the width. This is why I have taken. And in the vertical depth wise, for the depth you can take the, for the depth z, depth is like that. Just for you I want to draw something. This is the bed and this is the depth is indicated. I think hope the figure is understandable to all of you. So in the x direction, this is the x direction. Sometimes in case of flood, river flood, you have seen already on the surface something is moving like that and flow is, something is moving, some structure is rotating on the surface of the flow in the river, and propagate in the downstream. This is the flow of, this is the flowing by the this direction. So rotating in this direction, let's assume the rotating the anti-clockwise or sometimes clockwise also somewhere. It is depend on, and let's assume some breeze pair is all here. That's the breeze pair, and let's say the breeze pair. So what is happening? I want to show the breeze pair here. This is the breeze pair. This is the number one breeze pair. I want to show this is the number one pair. And in the widthwise, there is the number two breeze pair in the channel also. So due to the presence of some obstacle in the flow, in the flow domain, what is happening? What will happen? The rotation in the x direction is also possible. Whatever is, this is a high flow, that is a very turbulent flow in the, in case of in during the flow or during the flood, the very highly turbulent flow in the river system. So what will happen? The fluid particle it rotate in the x direction also. Fluid particle also rotate, will also rotate in the y direction, that is the lateral flow, that is the your velocity is having the three component you all know, u, v, w. That is the V is this direction, W in Z direction, and U in X direction. Here I am assuming. So in case of vertex also, vertex is possible in the X direction. Let's your X direction means that the water is moving like that and propagating in the X direction. In the Y direction, whatever is flowing in the Y direction, the vertex is Y direction is also. The vertex in Z direction is also possible. This is the actually meaning. The vertex in the direction. If possible, maybe. So I think Frederick, you got the what is the axis? What do you mean by axis here in terms of vortex? So now
Yes,
moving. Okay.
at the same, is this thing happening in the same time? I mean, is at the same time it is having rotation z direction, x direction, y. Oh,
Yeah, in the same time possible. Yes, why not? If you know the flow in case of very turbulence, in the same time, yeah, these are the phenomena happening in the river system at the same time. You are telling, I think, for the same particle. No, no, this is a not.
yes, sir.
No,
I
no,
mean the
no.
same
This is a
particle
not
and
say
having.
same particle. No, no. If your one particle is moving in the direction, how you can consider this direction? Maybe your same particle maybe follow like that. This is the particle path in case of laminar, but in case of turbulent, maybe this is the x direction. You can assume perpendicular is the y direction. So maybe this is the path of in case of turbulent. This is the random path. So here, if you draw the tangent like that, this is the x direction velocity. This is the y direction velocity component. Your fluid particle is moving in the which direction? X direction as well as in the y direction both. Are you getting? And might be chance it may be also in the your fluid particle is here maybe at in the next time the fluid particle in moving laterally and with the x direction also and vertically also. Are you getting? The same particle, this particle may chance to move in the straight also, but if moving like that, this particle is moving in the lateral direction little bit in the x direction, or little bit in the z direction also. So this is the concept behind the same fluid particle may be moving in the x direction, y direction, and the z direction also at the same time. Because x direction is like if your particle want to move in the x direction, that it follow this path. If your particle only moving in the y direction, just follow this path. If your particle moving in the z direction, this will follow only one path. But your fluid particle follow this path, so it is going in the x direction also, it is going in the y direction also, or maybe it going on the z direction also. The same fluid particle, Frederick, here the we are discussing about the same fluid particle uh, move in the x direction, y direction, z direction. It's depend on the flow condition how it is happening in the river system or the pipe flow. So now we'll discuss some more about the vortex flow. And what is free vortex flow? Free vortex flow means here not is the case of the vortex is not there in the system. This is not case. The definition is that a free vortex flow is a specific type of vortex flow in the fluid dynamic where the fluid particle rotated around a common center without any external force or disturbance acting on the system. Like if in the system, if you are not giving the any external force, without giving the external force, the if the fluid particle is rotating, if the fluid particle is rotating without giving any the external force, this type of flow is known as the free vortex. And the vortex flow is what? The vortex flow is what? It's having some external source. For, let's say, for example, I want to take more example, like you take one glass of water. For rotation, if you stir by like a spoon, then water is rotating like that in the glass. So this is the free, this is the not case of the free vortex, because you have some, you have put some the external or torque, or you can say the external rotation for rotating the fluid in the glass, but you are not giving from the any kind of force from the external source, and your fluid is rotating freely. So this type of flow is known as the vortex flow. And this what is, and now I want to move on the, okay, in the another words, it is a self sustaining rotational motion. Okay, self sustaining means there is no need the external source for the rotation, in which the fluid particle conserve the angular momentum. You all know the angular momentum is rotational thing, kind of things here. Okay, so now moving on the question, what is written in the option? A whirlpool, a whirlpool in the river. Let us assume a river system is like that. As water is flowing in this direction, what is happening? Let us assume this streamline is followed the path like that. So at this location, what will be happen? This here in the flow of river, the sediment as well as water is both. So here the some deposition thing is happening, and the outer bank will migrate like that. This is maybe migrate like that. In the next year, migrate like that, and having some more depth at that location. So this is known as the whirlpool. And in this, when you go on the field observation, and if you see, when you go for the river, and you and just observe what is happening in the river, you just see on the, this is known as inner bank. If you tell this is inner bank, this is all outer bank. At the outer bank, the rotational kind of things, rotational phenomena is happening. So without any force, you are not giving here any force due to the what, due to the shape of the river, this thing is happening. So this is the example of the free vortex flow. And another, let me check. Okay, the another is one is what, the option B, flow of flow of liquid through a hole providing at the bottom of container. Let us this container I have taken, and one hole is there. The lots of pressure here. When you open the container, then what is happening? You just uh, the flow is not like very smooth. When you observe, the flow is not very like, flow is like that some rotation kind of thing. That is the your streamline having some rotation, then having some rotation, not that much. So this is also a kind of, but here you also not giving the some external force for the rotation kind of thing. The option number C, what is, the flow of liquid around a circular bend in the pipe. where the bend in the pipe, this kind of phenomena also you can see. That is the same case what I have discussed here. So all option is correct for the question number 9. So I think hope you got the concept behind the free vertex and the vertex flow. So please go follow solve the question number 10. Okay, Ashok is telling the option number C is correct. The velocity potential, whatever we have discussed already, the velocity potential, the same concept here you can apply. This is the nothing but potential existence means what? This is the mathematically we have defined. Just we have given the name for something y potential, velocity potential. So please give your answer. I think time is also. Someone was asking about the initial, the book of the fluid dynamic kind of thing. What was the? Please give everyone answer in the chat box for question number 10. Then I have something, Fred Francis. I have so whatever you was asking in the previous classes, I have discussed already in the first like around what was the time around 6:20 or 30.
Sir, I will check the recording. I was not able to.
Yeah, recording, and also I have some. You can take the screenshot. I will show
Okay,
just
sir.
after discussing the question number 10. I will show the what I have discussed. You take the screenshot. If you will go through that. It is very well written in the Sinjal and Simpala book. I have taken the some screenshot from this book, and you just go through that. Your concept will definitely clear.
Okay, sir, I will do that.
Okay. Please everyone write your answer in the chat box. Okay, Matthew is telling the option D. Okay, all 3D flow. 3D means here the three-dimensional flow. Velocity potential exists. Okay, all 3D means here the flow may be the rotational, irrotational, compressible, incompressible. The all means here that the okay. And one student was asking about the registration fee. I think. Oh, you please contact the NPTL team. I think some help mail was there, and contact maybe contact email ID was there. You just mail. Otherwise, I think time is very less, very few days remaining. So you write the mail. Otherwise, may be difficult for you. Okay. For question number 10, let's see. Then I will show the some. Okay, for question number 10, before going the question number 10, I was discuss about the velocity potential. Let us move. Yes, here. Please take the screenshot. Then, if anyone want to take the screenshot, please take. So velocity potential is nothing but it is a mathematical term. There is the potential term is a mathematical term, but we are using in case of velocity. That's why we are putting the here the velocity potential. So what is the velocity potential is a concept used in the fluid dynamics to describe the relationship between the velocity field. Velocity field means x direction velocity, y direction, whether the in the pipe flow your water is flowing in x direction, that is 1D flow, whether 2D flow, that is x direction, y direction, whether 3D flow. This is the definition. The velocity field. This is the meaning of velocity field. Between the velocity field and a scalar function known as the velocity potential function. Okay. In the mathematics, it's a mathematical tool that simplify the analysis of incompressible, okay, irrotational flows, which are follow where the flow where the fluid density remain constant and there is no fluid rotation. So basically, we assume for the velocity potential the flow is incompressible and the rotational flow. So what is given in the option? Okay, velocity potential exists for flow of perfectly fluid only, no the steady and irrotational only. Here is written the only, so it is not the case, maybe wrong. The all rotational flow is the correct answer, option number C. You can go here. Some, I think all irrotational and the incompressible, some typing mistake I think. So option number C is correct with this correction. So Frederick, you can, Francis, I think. Just a moment. Yes,
Yes.
Francis, you can take the screenshot. I want to put it in the full view mode. You just take the screenshot of it. Just let me explain some because I have not time. I have the another's. Okay, you take the screenshot and go through that. This is the, your pitot 2 concept. You can take the screenshot.
Yes, sir.
And now your static pitot tube and pitot tube.
Yes, sir.
Okay, now you can take the also
Yes, sir. I did.
this one also. You can take the pipe roughness for was your no doubt whether the pipe roughness is affect the velocity and pressure. Yeah, velocity and pressure due to the pipe roughness, your velocity will be reduced and pressure also will be dropped. Both things will be affected by the roughness. Okay.
Yes, sir.
Okay, you go through these lines, you definitely will get. You can take the screenshot also.
Yes, sir.
So with this note, we'll meet in the next. We'll meet on next Monday. I think week number 6. I think week 6 is going on right now. Hello, week 6 is going on.
Yes, yeah.
Yes, sir.
Yeah. Okay.
It all is problem solving week, sir.
Yes.
It is a, yeah, week 5 is a problem solving.
Yeah, week 5 was, yes, today was the problem solving of week 5, but week 6 is going on. I think NPTEL course is going on week 6, no? Or week
Yeah,
7 is running.
it has
Which one is
notified.
running currently?
Yeah.
Week 6, okay. Okay, okay.
Sir,
Yes.
is the free vortex and for uh, just vortex and forced vortex same?
What you
Forced
are,
vo- forced vortex flow and uh, Just simply we say about if vortex flow, both are same.
Oh, you are telling the force vertex flow, right?
Yes, sir.
No, no, no. Force vertex flow is means what? Okay. Okay. No problem. Vortex flow basically is two type, basically force vertex or free vertex. So if somewhere is mentioned the force vertex flow, then it is fine. But only vertex flow is written, you can just it may be the free vertex and the force vertex. It depend on where is written. So only the force vertex flow is written. You cannot say the this is the force vertex flow. Okay, I think
So
somewhere I have telling about the vertex flow means no, this is not case. But if written in specifically force vertex, free vertex, then you can tell finally, yeah, this is the free vertex of flow. If only vertex flow is written, then based on your observation or concept, you can maybe find out maybe in this case the maybe vertex may be free or maybe force. It's depend on the case where it is happening. Yes, Francis.
so actually the vortex flow is divided into free vortex and forced vortex.
Yes.
The whirlpool and the flow in the sink will be free vortex, and if we stir a cup of tea, then it will be forced vortex.
Yeah, this is the just for example I have given. If you take maybe maybe your bent pipe is given, right? Maybe just for example is bent pipe is given. In the case of bent pipe, the vertex is happening without any giving the force, external force. And if you giving the force for creating the more vertex, the similar case may be the force vertex also. This is not. If you may be giving the some external force, so it may chance to your free vertex may be converted in the mixed type of vertex, free and force also. So this is
Okay, sir.
not
So,
only example and steering, but for the sake of understanding, just I have given the in case how the force vertex create generated. Yes,
so in
please.
the case of that whirlpool or in the flow in the sink, does it need to be? I mean, the fluid element. Or if you take a fluid element, it will be actually rotating about the axis of the whole of that sink, isn't it?
Yes,
Does
yes, yes.
does it need to rotate in any other axis if it is in the forced vortex?
No, you are telling when we give the force vertex, let's say the first system was about first system was the free vertex, then you apply the force on the same system, then you are asking about the whether the fluid particle change the direction or not, like that.
Yes, sir. If the it's actually rotating about one axis. I mean, if it is rotating, do it need to rotate in any other axis for it need to be forced vortex?
No. Just you try to understand what is actually I'm not getting correctly your question, but let me explain something. If your fluid particle, the axis means here, if your fluid particle only moving in the direction that is the x direction only, the straight way, so it is only the x axis, one directional vertex. If your fluid particle is moving like that, so what is happening here in the x direction also your velocity x direction also your fluid is moving, and y direction also, let's say the y direction here is what, the x direction is 0 and here y is also 0, but as you moving here the same fluid particle moving here, the y is something positive and x is something positive, so x is also increasing and y is also increasing, so same fluid particle may chance, let me explain, you are telling some fluid particle in the pi flow, let's say the bend, in here the vortex is happening. As you increasing the force, let's as you increasing the force, what it will happen? It may be the chance your fluid particle was moving like that. Maybe the chance it may be the moving like that. Maybe the yes, definitely it will may change the. It depend on the magnitude of the force. May change the direction or may not change the direction. So it's a case. It's depend on the case or scenario of the
So
force.
actually, we can compare this with the. I mean, if you are taking the planetary Earth and Sun as a system, I mean, if we consider the Earth as a fluid element, it's actually rotating its about in its own axis and it's actually rotating about the Sun, isn't it? So, since it is actually rotating its own axis, it's actually free vortex uh,
Yes.
and if it is rotating, since it is rotating about the around the sun, that rotation only we consider, then it's actually forced vortex.
Oh, no, no, you are asking. Please repeat again. Repeat again your, because I am not getting the completely what you are asking. Please repeat again.
So I mean, if you take the earth and sun system,
Yes,
actually
yes,
the earth is actually rotating about its own axis, and
yes,
since
definitely.
we can compare that with the free vortex, isn't it? Since it is actually rotating.
Yes, without any force, without any external force, the Earth is rotating. So that is a free vertex kind of thing. You just imagine. Yes, you can tell. Definitely, there is
And
no
it's
external
actually,
force.
but it actually rotating around the sun in a I mean, if we consider it as spherical path, elliptical or circular, it's actually rotating in a about the sun, isn't it? So can we compare that rotation to the force vortex?
No, no. Here, actually, in case of this, what you are telling, there is no external force is here. You just think there is no external force is applying on the system, whatever you Earth and Sun is telling. So this is a freely only the system is framing the system is like that. This is moving freely. There is no you just there is no case that is today is the earth is moving like that, and in the next day maybe it will be different. This is not this is a free vertex case only. There is no external force is working on that.
Actually, the gravity of the sun is actually acting on the earth, isn't it? So it will be like we are trying to steer a cup, we are applying force on that fluid element, and here the actually the gravity of the sun is actually on the earth, isn't it? That's why it's actually rotating around the sun, isn't it?
Yes, yes.
Can we say that rotation of earth around the sun as force vortex, and that spinning of the sun as free vortex? I just need to imagine.
Okay, you
Come.
want to correlate. Okay,
Okay.
so no, this is a Francis. This is a very big thing. So I cannot tell here. Uh, for that, you need. I think we need some lots of analysis. Without analysis, we cannot tell. So okay, if you have doubt like that, then definitely maybe you can. I will try in the next class. Don't worry.
Okay, sir. So,
Okay.
and there was one question that about the if we are plotting that datum line, energy line, and velocity head, then how the points will be arranged in an order? I mean, actually, the energy we have actually discussed about that energy, total energy head, and datum head and velocity head, isn't it? Last class.
Yes.
So if we mark it in a I mean, the which one will be order, I mean the if you take a point for the velocity head, then where it will be coming, it will be above the datum head or will be below the datum head.
No, no. The datum head is no, no. You are datum is it's depend on your choice where you want to take. Okay. Uh, this is maybe you can take the pipe flow. You can take the datum at that point. If you want to take the datum at that point, it's depend on your datum at that point. And also sign convention also depend on your choice also, whether moving the above direction it is positive, moving in the down direction, but throughout the your calculation and analysis the sign convention should be same, then you will at the end of the calculation you will get the exact answer. So it's depend on your sign convention, and also and the datum whatever you are talking, the whether the velocity, that is the velocity head, is above the datum or below the datum. So it's I think, let me explain. Your piezometric head is what? Datum plus pressure head. This is represent the HGL, hydraulic gradient line, and when you include the velocity head also, then it will increase. Then it will indicate the energy gradient line. That is the head is equal to here H also. Here head is equal to what? P plus P by rho z plus V square by 2z plus Z. All three, all three energy. So let's say your datum is here, and what will happen? Pipe flow is like that, and you are considering the datum at that in the first case. In second case, you are considering the datum at that point, and you
Uh,
considering, yes.
Sir, actually, they have asked about the order of each point. I mean the um, this datum head and velocity head and total energy head. So I mean if you consider the total energy, the major contribution will be given by the datum head. Is that like that? I mean the major contribution will it be given by the datum head,
No,
or it will
no.
be.
Datum head only, the concept is what, where you are taking. Let's say if you are, let's say you are measuring when you apply the. Let's me go on. You are, you want to calculate the pressure here and here, right? So this is the Z1, and this is the Z2. If you are taking the datum at that location, what will happen? Your Z1 will be 0. Here said Z1 having some magnitude, Z2 having some magnitude. Because you are, because your equation is derived only one streamline. So you want to calculate uh, on a single streamline the velocity and pressure whatever you want to calculate. So your datum, if you considering here having some magnitude, but if you considering the datum here, it will be 0, it will be 0. So if when you draw a pressure gradient line, what will happen if you taking, if you will take the datum at the center, then what will only p thing will be here, because but your datum should be straight here. So here what is happening, some z1 below, so here z2 is what, some minus magnitude is, right? So when you take the datum, it will be eliminate. There is a no hard and fast rule where you want to take the datum.
Okay, sir.
Yes. Okay, Freddy. So thank you all.
Thank you, sir.
Okay, okay, thank you. Regarding the problem 9, assignment 5. Okay, I will see. So I will see the assignment 5, question number 9, no problem. Let me note it down. Assignment 5, problem 9. Okay. I will see. Okay, thank you all. Thanks again.
Thank you, sir.
Okay, thank you.